Welcome back to the lectures. The Chemistry 1 is a series of lectures under the massive open online courses program and is being are being delivered to you through the NPTEL online courses program. So in this lecture, we have a brief summary of the Niels Bohr's atom, the de Broglie matter waves, and also the time-dependent Schrodinger equation. It's a sketchy introduction. More details will come later on the Schrodinger equation, but the purpose of covering the Bohr's model and the matter waves is to set the stage for the solution of the Schrodinger equation and how that's different and is more general as a quantum mechanical phenomenon. Okay. The lecture is, we'll start with a summary of the Bohr's atom. There are two assumptions that Niels Bohr made, and it's a famous paper in 1913 when he described his theory for the atomic structure or the structure of the hydrogen atom to explain the spectral series or the hydrogen spectral lines. It was one of the most important problems in the atomic domain that needed to be explained. And there are two assumptions that Bohr made. Both these assumptions were to get the picture of the atom with the electron moving around the nucleus in an orbit, in the case of hydrogen atom this being a circular orbit, and therefore led to, with these assumptions, an explanation of the hydrogen spectral series known as the Lyman series, the Balmer series, the Paschen series, the Brackett series, and Fund series, and so on. Now, let's see a small picture of the same. So, here is a picture from one of the IIT Kanpur websites on the ICT Wiki. I shall give you the acknowledgement in a separate sheet. The hydrogen atom spectral series are marked here as corresponding to different wave numbers, starting with the Lyman series, for which the highest wave number is 109,678 centimeter inverse, and then there are a whole series of lines with wave numbers smaller than that. This is one set of lines seen in the emission spectrum of hydrogen. The other is the Balmer series, which is about 1/4, exactly 1/4 of the Lyman series starting line, 109,678 divided by 4. This is the beginning of the Balmer series lines, and also there is a whole series of spectral lines, and likewise Paschen series, Brackett series, and Fund series. Rydberg had earlier recorded these, had earlier explained the spectra with a simple formula. The nu, this number 109,678 centimeter inverse, this is the wave number as 1 by n1 square minus 1 by n2 square. n1 is 1, 2, 3, etc. and n2 is always greater than n1, starting with 2, 3, 4, etc. Therefore, this is the prescription. This is purely an experimentally observed phenomenon and a fit provided, and Niels Bohr's theory was to explain this fit. Of course, it explained the fit beautifully, as we see it in a very quick summary. What are the two assumptions that Niels Bohr made to understand the spectrum of hydrogen? The first one, the electron in the hydrogen atom is confined to only those orbits, circular, for which the angular momentum of the electron, mvr, where r is the radius of the orbit and v is the velocity of the electron, radius, velocity of the electron, or the speed actually, mass of the electron. This mvr is n h by 2 pi, and n is an integer 1, 2, 3, etc. and h is of course Planck's constant. This is assumption 1. And it's easy to see that the angular momentum for a circular orbit is mvr, because suppose you do that and you write the radius vector as r and the tangential velocity v of mass m, then you see that r cross mv, which is r cross p, in this case is actually mvr, because r and p are perpendicular to each other. This is a vector cross product, and this is equal to nh bar, which is h bar is h by 2 pi. Okay. This is assumption 1. The second assumption that Niels Bohr made, which is even more crucial to the whole picture, is that electron being a charged particle and moving in an orbit, classically, if it were to behave classically, the electron would lose its energy, because any accelerating charged particle loses its energy as it accelerates. Therefore, the electron will not stay in a circular orbit. As it loses its energy, it will spiral into smaller and smaller and smaller circles, and eventually it will fall into the nucleus. Okay? The time taken for this spiraling to happen, when you calculate using classical physics, is an incredibly small number. Therefore, obviously that's not true, because the hydrogen atom has been stable for millions of years, at least ever since we started looking at them. The atom is a stable atom. And therefore, what Niels Bohr suggested was that when the electron is in one of these orbits, it does not lose any energy. It conserves its energy. No loss of energy is possible. Therefore, how do we get the spectrum? The spectrum happens when the electron goes from one of these orbits to another orbit, either due to the large amount of energy that the atom has when you heat the atom, or in an absorption spectrum when light shines on the hydrogen atom, the electron absorbs that energy and goes into another orbit. Therefore, to calculate that energy, Niels Bohr arrived at the energy of each of these orbitals through a very simple classical formula, which I will write. And the energy of each of these orbits with the quantum number n, he introduced the word quantum number n, and n being 1, 2, 3, etc. The expression for the energy through a very simple calculation, it's not the purpose of this lecture, but through a simple calculation, it turns out to be minus m e raised to 4 z square 2 pi square by h square into 1 by n square. M is the mass of the electron, E is the charge on the electron, the fundamental charge, Z is the nuclear charge, which is 1 in this case, and the H is the Planck's constant, and N is the quantum number given the values 1, 2, 3, etc. Therefore, the energy emission happens, you can see from this formula that when N is 1, this is the most negative, and the electron being in a bound state with hydrogen atom, the system has negative energy, and the most stable energy is the most negative energy. And if you calculate this energy by substituting all these numbers, En turns out to be minus 13.6 electron volt into 1 by n square. And this you can write in the form of Hc and the Rydberg constant into 1 by n square, and this Rydberg constant happens to be 109,678 centimeter inverse, roughly. Okay? There are small differences due to the reduced mass of the electron and so on, but it's approximately the same. Therefore, the success story of the Niels Bohr is that he, through his assumption, he arrived at the quantized orbits with energies E1, E2, E3, etc. And therefore, you can see that the energy level picture is that E1 is minus 13.6 electron volts, n equal to 1. And if you say n equal to 2, then if you put n equal to 2, the orbit has minus 13.6 by 2 square 4 electron volts. And for n equal to 3, of course, it is minus 13.6 by 9. So if this is the increasing scale of energy, you can see that at some point, if this is minus 13.6, you can see that the energy reaches 0. This is the 0. And for this, n equal to infinity. Therefore, the energy levels are such that the lowest energy level is minus 13.6 electron volts, and the next one is 1/4 of that, and the next one is 1/9 of that, and so on. And then Niels Bohr could say that the electrons, when they jump from one orbit to another, if they go up, they absorb the energy because the orbits of higher n have higher energies, less negative, higher values, positive values in that sense. Therefore, that's the absorption spectrum, and the emission spectrum is when n, the electron from a higher n falls into a lower n. And you can see that from any n it can go to any other n, and therefore you can see everything that drops into 1 from any of these levels is a line that corresponds to a Lyman series line. Everything that drops into 2, n equal to 2, from higher levels forms a Balmer series line, and then there is the Paschen series line and Broglie series line and Fund series lines. These spectra are beautifully seen in some of the pictures here. You can see the Lyman series line. Okay, the Lyman series lines are all near the 100 nanometer wavelength. What we had was 109,678 was a wave number. It's a centimeter inverse 1 by the wavelength, but in terms of wavelengths, it's 100 nanometers around. And then you can see that the Balmer series lines are all here in the visible spectrum, and then there is the Paschen series lines which are all here again in the visible spectrum, and then there is the bracket series corresponding to higher values of n1 and n2, and then the Fund series and so on. So this is the actually observed hydrogen atom spectrum that Niels Bohr was able to explain. But then what are the difficulties with such a model? The difficulties are that only the spectrum of hydrogen could be explained this way, hydrogen atom. And also field free. If the hydrogen atom were to be put in an electric field or a magnetic field, the spectral lines become doublets, and there are issues. If you have to take this to other atoms like the helium atom and so on, you needed not a circular orbit but a slightly more general orbit, and it was Professor Arnold Sommerfeld who proposed elliptical orbits. Elliptical orbits have two axis system, the major axis and the minor axis, and therefore can in principle correspond to two quantum numbers instead of the single quantum number that Niels Bohr introduced for the angular momentum, nh by 2 pi. Instead of that, you can have two of them. But then what's the point of these kind of extensions without any real theoretical basis for that? So there were questions about the extendability or the applicability of the Niels Bohr model, despite the fact that it was a spectacularly successful model in predicting the hydrogen spectrum and associating a fundamental an atomic formula for the constant known until then as an arbitrary constant, the Rydberg constant. Okay. Therefore, given that some generalization of all these things from a more fundamental level was needed, and I think soon after that it was Louis de Broglie who came up with a postulate, namely that all matter can be wave-like as well. That is, matter which is localized or which is particulate, things move and you can follow the movement as movement of the particles. In motion, such matter can also be associated with the wavelength. And de Broglie called this phenomenon as the phenomenon of matter waves, and it is an important extension since until then people believed that matter is either wave-like or particle-like, with the exception of light, because light was shown to be particle-like in the sense it's the assumption that light is small packets of energy was used to understand photoelectric effect, and later many experiments were done to suggest that light could be particle-like. And then of course electromagnetic radiation was known as a wave phenomenon ever since the theory of diffraction and interference were known, and therefore light was the only thing which had both particle-like behavior and wave-like behavior. And de Broglie's idea was that it's not just light, it's all matter. For that matter, electron can be a wave-like, can also have a wave-like attributes, can also be particle-like attributes, and so on. Therefore, de Broglie proposed the matter waves, and he proposed a wavelength for the matter waves in motion, and he arrived at this formula where P is mv non-relativistic motion. Okay. For our case, we will only worry about the non-relativistic motion, but h is the Planck's constant again. And the association of a lambda with a concentrated or a localized mass entity during motion was seen as a new phenomenon, seen as a new type of matter or material, and this led to questions whether such matter waves can be actually detected or do they exist, and so on. We will see later towards the end of the lecture that there was the experiment by Davison and Germer, electron diffraction experiment, very famous one, around 1927, which showed that electrons could be actually diffracted through passing through a crystal, and therefore the electron exhibited the properties of a wave. Until then, the Millikan's oil drop experiments and many others had confirmed that electron was a particle, was a localized mass, and so on. But then electron diffraction experiments showed that electron also had the same property as light. It can be both wave-like and particle-like. Then with this prescription, it was Schrodinger who therefore asked the question, if substances are like particles and they obey Newton's equations for particle motion, and if substances are like wave and they obey the wave equations or the equations of Maxwell, what do these matter wave quantities behave due to? Is there a separate equation which governs them and which in the right limit can go to that of a wave equation or that of a particle equation? So Schrodinger asked the question whether there was a separate equation for the matter waves, and within a few weeks of this question, after studying de Broglie's thesis, Schrodinger came up with the formula that he said all atomic fundamental particles satisfy this equation in time with a function psi, and let me read that out. It's I h by 2 pi, the time derivative, partial time derivative of a wave function psi, which is a function of time and a set of all coordinates of the particle, and it's equal to this derivative multiplied by I h bar is equal to the action of the total energy of the system, which may depend on time and will of course also depend on the positions because of its the potential energy and the kinetic energy and so on, and therefore you have its action on the wave function x. So it's I h bar d psi by dt, dou psi by dou t is equal to h psi is the most fundamental equation of matter, which was proposed in 1926, equation known, and 1926. And Schrodinger proposed this 1 year after the another group from Germany in Göttingen came up with an explanation of the hydrogen atom spectrum and the general framework for the atomic mechanics using matrices. So there were two groups of quantum mechanical descriptions at that time. The matrix mechanics was proposed. Matrix mechanics used the idea of matrices for quantum mechanical quantities, and it was proposed by Heisenberg, Max Born, Werner Heisenberg, Max Born and Pascal Jordan. And this is the wave mechanics proposed by Erwin Schrodinger. And it was eventually, this was 1925, this is 1926, and it was eventually Schrodinger who connected the matrices with the wave mechanics through his famous formula that the momentum represented by, in the matrix mechanics, the operator for the momentum provided by Heisenberg and others is the same as the derivative minus I h bar dou by dou x, if I have to write this in the x component of the momentum, or if in any other coordinate system, if the momentum is given in that coordinate system, it's a derivative minus I h bar dou by dou of that coordinate. Okay. This formula was also established by Schrodinger, establishing the connection between the two different approaches and solving not only the hydrogen atom problem, but proposing this equation as the most fundamental equation of matter for the study of atomic systems and systems for which the classical methods, the classical mechanical, statistical mechanical, and the classical electromagnetic theory were not giving satisfactory answers. This was proposed as the most fundamental equation, and the Schrodinger's equation has stood the test of the time for the last 95 years. There are no questions about its applicability until now, except that one has to discover more and more phenomena, newer and newer ways of solving the differential equation. Please remember, this is a differential equation, and the matrix mechanics proposed the matrix eigenvalue problem solution as the possible method for solving quantum mechanical problems, and these two methods were ultimately the most important ones which had been proposed in the last century, at the turn of the last century. And let me complete this lecture with the following statement, that it's not this equation that I would solve in the rest of the course. I would love to, but it's a little bit difficult, and it requires other technical details of how to solve differential equations with the Hamiltonian dependent on time. So let me write this equation. When the Hamiltonian is independent of time and is only dependent on the position coordinates, this can be written down into two component equation, one for a time variable and one for the position variable, and the position variable equation gives a function psi of x. Please remember, this is different from this function. This function is dependent on time and position coordinates. This is a wave function which depends only on the position coordinates, and this is equal to E psi of x. This is time independent Schrodinger equation, but this time independence relates to the fact that the Hamiltonian is time independent. What is meant by Hamiltonian being time dependent? For example, if you shine light on a system and you are studying while light is, or the electromagnetic radiation falls on the system, the energy of the system is not a constant, because the radiation itself is an oscillating electric and magnetic wave in time, and therefore the radiation has time dependent energy contribution while it's present in the system. Therefore the Hamiltonian for such a system is time dependent. The other example is that we may introduce a force, a time-dependent force, for a brief period of time and then follow the evolution. So what happens during that process? So the Hamiltonian can depend on time in principle, but we will study only in this course in a very elementary fashion. We will study only those Hamiltonians which are time independent, and for time independent Hamiltonians, this equation reduces to what is known as a time independent Schrodinger equation, and this is what we need to look at. Okay? The rest of the course will study partly some introductory spectroscopy where time is important, and model problems such as particle in a box, Schrodinger, the harmonic oscillator, and hydrogen atom examples, not in a complete mathematically solvable form, but we will try to understand the principles behind the solutions rather than the solutions themselves. It's an elementary course, therefore we will try and concentrate on the solution of the time independent Schrodinger equation for a few simple systems. The next couple of lectures we shall introduce what is the spectra, what is spectroscopy and what we study in spectroscopy, and then the week following that we will start looking at the solutions of the Schrodinger equation. Until then, thank you very much.